Bell's reasoning is still correct. The two have to depend on each other, but they occur at the same time and place. So there's no non-locality implied. The explanation of the sign-squared dependence is straightforward. Suppose we want the frequency with which both particles will be observed to be vertically polarized. The vertically polarized wave from one measuring device will come in and form an angle theta with the vertically polarized wave from the other side. These two waves together will form an amplitude for emission of the particle pair, and the amplitude will be proportional to sine theta over 2. That's the amplitude. But the probability of emission of the pair is proportional to the square of that amplitude. So you get sine squared theta over 2. And similarly for any other pair of these waves. So we get the correct sine squared relationship with a completely local explanation. I'm sorry, say that again?
What you're trying to say is you annihilate all the electrodynamics involved in the emission of photons from atoms.
I'm sorry, I still didn't hear. No, what involved?
There is no electrodynamics involved in that. There is nothing like electric fields or anything involved in this process. Reverse traveling waves do everything.
You're asking really where these waves come from how the waves are emitted by the two measuring devices?
No, the forward wave theory assumes that there is some electrodynamics involved in the atoms, where somewhere the photons are emitted.
Oh, I see.
You are superseding all that.
No, there definitely will be waves and electrodynamics involved, and I'll talk about that later when I look at Feynman diagrams. There'll be a specific Feynman diagram that will involve the waves from the two sides and waves in the atom that's doing the two-particle cascade emission. And it'll look almost identical to what current theory says. I'm going to talk later about atoms if we have time, and I will show in the case of atoms that in fact you can picture atomic processes also in a totally classical manner with particles following these waves.
Can these particles be emitted even if there's no detectors present?
No, what? I'm sorry?
Can these particles be emitted even if there are no detectors present?
Yes, they can, but that would simply mean that the waves would be coming from something else. These waves are always around. I'm going to talk about that more later also. All of the available states, in effect, are full all the time. It's just that out in space, away from any particles, they're completely disorganized. It's only when you're close to particles that the particles' action will organize them into larger pieces. And in this case, the particles in the detectors will organize those waves and give you the vertical and horizontal polarization. A rule you can...
The source and nothing else, the source could not emit. That's what...
No, I'm saying the waves...
In the universe, just a source containing no other matter, just vacuum, and a source sitting in the middle of this hypothetical Gedanken universe.
Well, it wouldn't be a vacuum. It wouldn't be a vacuum. The point is that these waves are there all the time. All of space is always full of these waves.
So the vacuum of space is emitting the waves in addition to the detector?
It's not emitting them. They're there all the time. They're what fill up space.
So you're saying, I just want to get a model. So empty universe has only a source. It would emit.
It would emit, yes.
May I suggest that we hold off on a lot of these questions, because I think the theory is presented in layers, and a lot of these questions I think will be answered, and we'll save, and we'll actually have more time later.
That's true.
Reserved for questions.
Some questions have to be asked. They must be asked.
Yeah, some of them need to be asked now, I'm sure, for clarity.
Can you wrap it up in 5 minutes so we can ask questions?
No. The best part is still to come. The best part of what time are we getting to?
It's 10:30.
It's already 10:30?
25.
Oh my heavens.
Straight back.
Can you stay later?
I can stay as long as you want, but I had no idea it was so late already. I'm sorry, I haven't given this talk before, so I had no idea how long it was going to take. I'm going to have to... I want to at least get one or two more things said here, because, as I say, the best part of what this explains I still have to do yet. I've been talking much too slowly. All right, with delayed choice, I'm going to have to go quickly over some of these things. With delayed choice, if one of these things is rotated after the particles, or both of them are rotated after the particles are already moving, the particle is going to have to jump waves as it's traveling across. It'll be following one wave part of the way, and it'll meet a new pair of waves in a new orientation. But in this theory, everything is deterministic, including the way the particles will jump. Now, because the two particles are created together as a single event, the parameters in each particle that determine which way they're going to jump are related to one another between the two particles. So, for example, if you were to rotate both polarizers by the same amount, both particles would always jump in the same direction as one another because of the relationship between the parameters in the particles. So if they both jumped in the same direction, that's equivalent to just rotating the whole system in the other direction, which is not going to change any of your statistics. See, the quantum mechanical distribution is already created at the source. Any jumping process just has to preserve that already quantum mechanical-like distribution. And for any of the experiments that have been done, that's exactly what will happen. Putting it abstractly, no matter how you rotate the polarizer, because the jumping process is deterministic, you know already at the source exactly how the particle is going to respond. So everything is still determined at the source when the two particles are together. So there's no non-locality even when you rotate the things while the particles are moving. I have to mention that, observe that in this explanation, there are no entanglements between these two waves. There's no need to use any entangled wave functions. Any entanglement, if you will, is just the way the two waves act together in stimulating the emission of these pairs. Current theory, there have to be entanglements because, well, everything is resolved, if you will, when you do the squares. And the squares of the functions are done at the two polarizers in current theory. So the entanglement has to be carried by the waves. But nothing like that is necessary in the reverse wave theory. And I guess I won't have time, but if I did, I'd show you later on that all of quantum statistics can be explained without any wave entanglements, including, and no need for any Fock space to explain Fermi-Dirac and Bose statistics. Now, Bell's theorem is generally interpreted as demonstrating the non-locality and as therefore demonstrating the weirdness of quantum mechanics. But in fact, it actually demonstrates exactly the opposite. Non-locality would mean the instantaneous interaction of two widely separated events by no physical means. That's impossible. It's a contradiction. You can only have an effect if it's produced by some real means. So Bell's theorem doesn't prove that EPR experiments can't be explained without non-locality. Bell's theorem proves that you can't explain EPR experiments, period, in a forward wave theory. So barring the possibility of any third theory in addition to the reverse wave theory, Bell's theorem, by refuting the forward wave theory, it really constitutes another proof that the waves move in reverse.